Hello viewers. Today we are going to discuss ANOVA. In ANOVA, we will first discuss when to use this tool. Then I will also be focusing on how does this test work. Then what are the basic assumptions of this ANOVA? How to perform one-way ANOVA. Then I will also discuss with you how to interpret the results. In detail, I will be also discussing about the post hoc testing. And at the last, I will be discussing with you what are the frequently asked questions about one-way ANOVA. So let's say what is one-way ANOVA. So it is simply we can say it is a analysis of variance, and as we are doing it one way, so we call it as one-way analysis of variance, and it is a statistical method for testing for difference in the means of three or more groups. Okay, so we can again, I'm emphasizing that it is a statistical test which is used to analyze the difference between the means of two or more than two groups. Okay, basically, if we see one-way ANOVA uses one independent variable, while a two-way ANOVA uses two independent variables. Okay, so now you can ask me, how is one-way ANOVA used? So the answer is one-way ANOVA is typically used when you have a single independent variable, or we call it as a factor also. And then your goal is to investigate if variations or different levels of that factor have a measurable effect on a dependent variable. So this is when and how the ANOVA is used. Now let's consider some limitations of this test before we proceed for the test. So one-way ANOVA can only be used when investigating a single factor and a single dependent variable. So this is one limitation. When comparing the means of three or more groups, it can tell us if at least one pair of means is significantly different, but it can't tell us which pair. Also, it requires that the dependent variable be normally distributed in each of the groups and that the variability within the groups is similar across the groups. Not only this, I have also brought to you a small chart which can tell us at what point of time, depending on our type of the variables, which test should be used. So here, as you can see, uh, we have two types of variables, categorical, okay, or we call it as predictor variables also, which can be categorical or quantitative. So let's first identify what type of variable we have, whether it is categorical or it is quantitative. Suppose if you say I have categorical variable, okay. So here we choose categorical. Okay, again it can be what is the outcome of the variable. So outcome of the variable again can be categorical or quantitative. So if we identify that it is categorical, the outcome is also categorical and the variable is also categorical. Obviously, what do we do then? So and if what do we do when it is a quantitative? Okay, so if it is a categorical, we will choose a non-parametric test. And if it is outcome is also quantitative, then we will do a comparison of mean test. So this is how many groups are being compared. Now that should be the question to us. Okay, two or more than two. So if we say only two groups are there, then we can use t-test. If more than two are there, then how many outcome variables we have? Now that we need to identify. So if we have one outcome variable, we will use ANOVA, that is one way variance analysis. And if there are more than one outcome variables, then we will use MANOVA, that is multi variable analysis. Okay. Now similarly, coming back to if our predictor variable is quantitative. So let's see what is the outcome variable then. Whether it is again categorical or it is quantitative. If it is categorical, we will use logistic regression. If it is quantitative, we can Again, say how many predictor variables we have, one or more than one. So if it is one, we will use simple regression. And if it is more than one, then we will go for multiple regression. This I discussed because we might be proceeding with ANOVA or two-way variance, or we can say MANOVA, but sometimes we are not able to do it on the right type of the predictor variable. So it is very important to identify what is the predictor variable, categorical or quantitative, and then what is the outcome variable, categorical or quantitative. So based on that should be our choice of the test. Now let's understand when to use a one-way ANOVA. We will use one-way ANOVA once we have collected the data which is based on one categorical independent variable and one quantitative dependent variable. So the independent variable should have at least three levels. That means at least three different groups or categories should be present. ANOVA will tell us if the dependent variable changes according to the level of the independent variable. Let's understand this concept by few examples. Let's say we have social media usage as one variable, okay, and which is independent, and we assign different groups like low, medium, and high levels of social media, and we want to find out if there is a difference in hours of sleep per night. So we will have three categories like low, medium, and high levels of social media usage based on the how many hours of sleep the individual is taking. Another example we can take where the variable is a brand of soda and we collect the data on Coke, Pepsi, Sprite, and Fanta to find out if there is a difference in the price per 100 ml or not. So here, if we take another example, like the type of the fertilizer. So we treat our crop fields with mixtures 1, 2, and 3 to find out if there is a difference in the crop yield. So in all these cases, we can have the null hypothesis of ANOVA. So the null hypothesis, which is denoted by H0, is that there is no difference among the group means. And the alternative hypothesis, that is HA, is that at least one group differs significantly from the overall mean of the dependent variable. So if we want to compare two groups only, we can use a T group instead of using the ANOVA. But if we want to use for more than two groups, then we will have to go for ANOVA. So ANOVA determines whether the groups created by the levels of the independent variables are statistically different by calculating whether the means of the treatment levels are different from the overall mean of the dependent variables. Now, if any of the group mean is significantly different from the overall mean, then the null hypothesis is rejected. So ANOVA uses the F test for statistical significance. So this allows for the comparison of multiple means at once because the error is calculated for the whole set of comparisons rather than for each individual two-way comparison, which would happen within a t-test. So the F-test compares the variance in each group mean for the overall group variance. Now, if the variance within the group is smaller than the variance between the groups, the F-test will find a higher F value and therefore a higher likelihood that the difference observed is real but not due to chance. Now, there are few assumptions of ANOVA. So, the main assumptions are independence of observation, normally distributed response variable, and the homogeneity of the variance. So, let's understand one by one what are these assumptions. So let's say independence of observations. That means the data were collected using statistically valid sampling methods and there are no hidden relationship because we have a confounding variable that we need to control for statistically use an ANOVA with blocking variables. Second assumption is normally distributed response variable. So the variable of the dependent variable or we say the values of the dependent variable follows normal distribution. Third assumption is homogeneity of variance. The variation within each group being compared is similar for every group. So if the variances are different among the groups, then ANOVA probably isn't the right fit for the data. So keeping first, we should go for these testing of the assumptions. If these assumptions are fitting in our data set, then only we should proceed for the ANOVA test. Now, one way ANOVA, as we can see, is the test for differences in group means. So it is a statistical method to test the null hypothesis, that is H0, that three or more population means are equal versus the alternative hypothesis that at least one mean is different. So we use the formal notation of a statistical hypothesis. For K means we write, as we can see on the screen, H0 is equal to mu1 is equal to mu2 is equal to, so we can say as many number of groups we have, so it is mu k, so till k number, and that says that the means of all the groups are the same. There is no difference between the means of the group. But alternative hypothesis says that not all means are equal. So here we can say mu I is the mean of the ith level of the factor. Okay, so we might be thinking, in what situation do I need to determine if the means of the multiple populations are same or different? In what condition? So let's understand this by a common scenario. This is like we suspect that a particular independent process variable is a driver of an important result of that process. So we may have suspicion about how different production lots, operators, or raw material batches are affecting the output. That is our quality measurement of a production process. So to test this suspicion, we can run the process using three or more variations. Okay, so of this independent variable, that is Ka factor, and then take sample of observations from the results of each run. So if we find differences when comparing the means from each of the observations using an ANOVA. So we are assuming here, please keep in mind that we have done everything correctly. Okay. So we have evidence that our suspicion was correct. The factor which we investigated appears to play a role in the result. So I will work out an example with you. Imagine that we work for a company that manufactures an adhesive gel that is sold in small jars. Now, the viscosity of the gel is important. Like too thick and it becomes difficult to apply, and too thin and its adhesiveness suffers. So we have received some feedback from few unhappy customers lately complaining that the viscosity of our adhesive is not as consistent as it used to be. So we have been asked by our boss to investigate. So what to do then? So the first step is that we will be examining the average viscosity of the 5 most recent production lots. That is the first step. Now, if we find differences between lots, that would seem to confirm the issue is real. And it might also help that it will also help us to begin to form our hypothesis about the factors that could cause inconsistencies between the lots. So we measure the viscosity using an instrument that rotates a spindle immersed in the jar of an adhesive. Now, this technology yields a measurement called as torque resistance, and we just test 5 jars selected randomly, and each of the we find that and they are from the recent 5 lots. Okay, and we obtain that the torque resistance measurement for each jar and plot the data. So we can see over here the torque resistance versus lot, and this is the chart before us, and here is the table also showing the mean of the five different jars. Now, from the plot of the data, we can observe that torque measurement from the lot of the three jars tend to be lower than the torque measurement from the samples taken from the other lots. So, when we calculate the means from all measurements, we see that the mean torque for lot 3, that is 26.77, is much lower than the other four lots. So, each with a mean of around 30. Okay, so here we have the ANOVA table. The ANOVA results are typically displayed in an ANOVA table, and this table includes like source, that is the sources of the variation, including the factor being examined. Like in our case, it is lot, and it can have error and total also. Then DF, that is the degrees of freedom for each source of variation. Then we have sum of squares, that is sum of squares for each source of variation. Mean square divided by its associate degrees of freedom, that is the mean square. So we have the sum of the squares. F ratio, that is the mean square of the factor, that is the lot, divided by the mean square of the element. So then we have probability, that is F, the p value. Okay, so these things you will find in the ANOVA table. So now let's see what are the components of this table and how these components are derived. Now, among these elements, you will find that the one of the key element is the p-value. The p-value is used to evaluate the validity of the null hypothesis that all the means are the same. So, in our example, the p-value, that is 0.0012, as you can see in the table. Okay, so this is very small. This small p-value can be taken as evidence that the means are not the same. Our samples provide evidence that there is a difference in the average torque resistance values between one or more of the five lots. So now before we understand or like accept or reject the null value, null hypothesis, we need to understand what is p-value. So p-value is a measure of probability used for hypothesis testing. The goal of the hypothesis testing is to determine whether there is enough evidence to support a certain hypothesis about our data or not. So if we recall from the ANOVA, we formulated two null hypotheses. We formulated two hypotheses. One was the null hypothesis and the other was the alternate hypothesis. So null hypothesis said that all means are equal, and alternate hypothesis said that means are not equal. So because we are only examining random samples of data pulled from whole population, there is a risk that the means of our samples are not the representative of the means of the full population. So the p-value gives us a way to quantify that risk. It is a probability that any variability in the means of our sample data is the result of pure chance. So more specifically, it's the probability of observing variances in the sample means at least as large as what we have measured when in fact the null hypothesis is true. That means the full population means are in fact equal. A small p-value would lead to reject the null hypothesis. So a typical threshold for rejection of a null hypothesis is zero point 0.05. That is, if we have a p-value less than 0.05, we would reject the null hypothesis in favor of the alternative hypothesis, so that at least one mean is different from the rest. So based on these results, now we can decide to hold lot 3 for further testing. So as we have seen in our report, we may write that the torque from the 5 jars of product were measured from each of the 5 most recent production lots. And ANOVA analysis found that the observations support a difference of data that shows that lot 3 had a lower mean, that was 26.77 talk, as compared to the other 4 lots. So we will hold lot 3 for further evaluation. Now let's do one-way ANOVA calculation. So as we have considered that our talk measurement example, and we will take this further in detail. So we will again recall that we had 5 lots of material, and from each of that we randomly selected 5 jars of testing. Now this is called one factor design. So one factor, that means the lot has 5 levels. Each level is replicated 5 times. Replicated means tested. So the results of the testing are here, as we can see in the table. Mm, jar 1, jar 2, jar 3, jar 4, and the mean values for the lot 1, lot 2, lot 3, lot 4, lot 5. So here, ANOVA test will not tell us which mean or means differ from others, or we can say unlike we have done it in the previous example. This isn't always obvious from plot of the data. So one way to answer questions about specific types of data or differences of data is to use a multiple comparison test. Now we can take to compare groups mean to overall mean. We can use analysis of means also, that is ANOVA. Now, to compare individual pairs of means, we can use Tukey-Kramer multiple co-comparison test. Let's understand sum of squares. So here you can find on the screen the formula, that is sum squared total is equal to sum squared of the factors plus sum squared of the error. So here you can see on the screen certain abbreviations. Let's understand what they stand for. So Ni, that is the number of observations for treatment. I, in our example, it can be lot I. Capital N, that is the total number of observations. Yij. So the jth observation on the ith treatment. Then Y bar I, that is the sample mean for the ith treatment. And Y bar, that is the mean of all the observation, and which is the grand mean. So putting all these things in the formula, we can see it on the, that is summation Yij minus Y bar whole square is equal to summation Y bar I minus Y bar whole square plus Yij minus Y bar I, that is whole square. Okay. So with these definitions in mind, let's understand the sum of the squares column from the ANOVA table. The sum of the squares gives us a way to quantify variability in data set by focusing on the difference between each data point and the mean of all the data points in the data set. The formula, as we have seen below, uh, uh, the partitions the overall variability into 2 parts. One is the variability due to the model of the factor levels and the variability due to the random error. So that is why I said SS of the factor plus SS of the error is equal to SS of the total. So while the equation may seem complicated, focusing on each element individually makes it much easier to grasp. Now, if we recall in our ANOVA table, the source column lists 2 sources of variation. So factor in our example lot and the error. So another way to think of these 2 sources in between the group variation means which corresponds to the variation due to the factor or the treatment, and within the group variation which corresponds to variation due to the chance or error. So using that terminology of our sum of the squares formula, it is essentially calculating the sum of the variation due to the differences between the groups, that is the treatment effect, and the variation due to the differences within each group, that is unexplained differences due to chance. So here is the ANOVA table, sum of squares, and we can see the SS of the factor is 45.25, and SS of the error is 32.80, and SS of the total is 78.05. So this is how the calculations are done in the table. Now let's understand the degrees of freedom. So, associated with each sum of a square is quantity called as degree of freedom. And the degree of freedom indicates the number of independent pieces of information used to calculate each sum of squares. For one factor design with a factor at k levels, like we have 5 lots in our example, and a total number of observations, like 5 jars per lot for a total of 25. So the degree of freedom will be as follows. See, the SS for the factor, that is k minus 1, so it becomes 4. SS for the error, that is n minus k, so 25 minus 5 is 20, and total SS will be n minus 1, that is 25 minus 1, that is 24. Now let's understand mean squares and F ratio. So we divide each sum of the squares by the corresponding degrees of freedom to obtain mean squares. Now when the null hypothesis is true, the means are equal, that is the MS factor and the MS of the error. They are both estimates of error variance and would be about the same size. So their ratio or the F ratio would be close to 1. And when the null hypothesis is not true, the MS factor will be larger than the MS of the error, and their ratio will be greater than 1. So in our additive testing example, the computed F ratio, that is 6.90, presents significant evidence against the null hypothesis that the means are equal. As you can see in the table also, some of the squares, degrees of freedom, mean squares, and the F ratio. So sum of the squares is 45.25, degree of freedom then in that case is 4, and mean squares is 11.31, and the F ratio is 6.90. While in case of the sum of the squares of the error, the sum of the squares of the is 32.80, degree of freedom is 20. So dividing it, we will get the mean squares, that is 1.64. Okay, so this gives us enough evidence whether our null hypothesis should be accepted or rejected. As you can see from the graph also, the F ratio, it gives us the values, we can see the density and the F ratio. Okay, so here the ratio of MS of the factor to MS of the error, they has an F distribution, and the F distribution is the distribution of the F values that we had expect to observe when the null hypothesis is true. That means are equal. So F distribution have different shapes based on two parameters, which we call them as numerator and denominator, that is degrees of freedom. So for an ANOVA test, the numerator is the MS factor. So the degrees of freedom are those associated with the MS factor. Now the denominator is the MS error. So the denominator degrees of freedom are those associated with the MS error. So if we compute F ratio and it exceeds the expected value from the corresponding F distribution, then assuming a sufficiently small p-value, we would reject the null hypothesis that the means are equal. And the p-value in this case is the probability of observing a value greater than the F ratio from the F distribution when in fact the null hypothesis is true. Now let's perform one way ANOVA. So here some data set is given to you, and we are taking an example of the fertilizers. Okay, so although with few observations it is difficult, but we will perform the analysis in the R statistical program because it is free and it is powerful and it is widely available. Okay, so even if you don't know the R, it is not an issue. You can do it on SPSS also. Okay, but those who know it, for them, this example will help out. Okay, So the sample data set is like imaginary crop yield experiment. Okay, so here we have fertilizer type. There are three types of fertilizers: type 1, type 2, type 3. Then we have planting density. So it is 1 and 2. 1 is low density and 2 is high density. Then we have planting location. So in the field, that is block 1, 2, 3, or 4. And then final crop yield in bushels per acre. So this gives us enough information to run our various different ANOVA tests and see what model is the best fit for the data. So for the one-way ANOVA, we will only analyze the effect of fertilizer type on crop yield. So the ANOVA output provides an estimate of how much variation in the crop, you can say, it is going to be variable that can be explained by the independent variable. So the first column lists the independent variable along with the model residuals, that is ACA, the model error. The DF is the degree of freedom, okay, for the independent variable, and calculated by taking the number of levels within the variable and subtracting by 1. And the degrees of freedom for the residuals, calculated by taking the number of observations minus 1, then subtracting the number of levels in each of the independent variables. Sum squared, this is the sum of squares, okay, of the total variation between the group means and the overall mean explained by that variable. So sum of squares for the fertilizer variable is 6.07, while the sum of squares of the residuals is 35.89. Mean square column, that is the mean of the sum of the squares, which is calculated by dividing the sum of the squares by the degrees of the freedom. We have already done it in the previous slides. The F value column, that is the test statistic from the F test, the mean square of each independent variable divided by the mean square of the residuals. The larger the F, the more likely it is that the variation associated with the independent variable is real and not due to chance. So then comes the p-value. This shows how likely it is that the f value calculated from the test would have occurred if the null hypothesis of no difference among the group means were true. So because the p-value of the independent variable, that is a fertilizer, is statistically significant, so that is p is less than 0.05, it is likely that the fertilizer type does have a significant effect on average crop yield. Now, doing the post hoc testing. So ANOVA will tell us if there are differences among the levels of an independent variable, but not which differences are significant. So to find out the treatment levels differ from one another, we perform a 2K HSD, that is honestly significant difference post-op test. The 2K test runs pairwise comparisons among each of the groups and uses a conservative error estimate to find the groups which are statistically different from one another. So here is the output of the 2K HSD test. It looks like this, as you can see. I'm putting the highlighter. First, the table reports the model being tested as fit or not fit. Okay. So next, it lists the pairwise differences among groups for the independent variable. Then under the fertilizer section, we can see the mean difference between each fertilizer treatment and lower and upper bounds of the 95% confidence interval, that is LWR and UPR, and the p-value adjusted for multiple pairwise comparisons. So the pairwise comparisons show that the fertilizer 3 has a significant higher yield, as you can see. It has yield than both 2 and 1. But the difference between the mean yields of 2 and 1 is not significantly, you can say statistically significant. So let's just see 2K HSD test. So 2 is to 1, difference is 0.176, and WR is 0.193, UPR is 0.54, and p value adjusted is 0.495. Okay, so likewise we have 3 is to 1 and 2 is to 3 also. Now the results of the ANOVA, let's see how they can be reported. So when reporting the results of the ANOVA, we include a brief description of the variables which we tested, the F value, the degrees of the freedom, and the P values for each independent variable, and then we explain what the results mean. Like we can see in this graph of the ANOVA. Okay, so we can also include a graph of the ANOVA results with grouping letters above each level of the independent variable, which to show which groups are statistically different from another. Okay, apart from that, while reporting the results of one-way ANOVA, we can see a significant difference in average crop yield according to a fertilizer, that F2 9.073, which is greater, we can see it is P is less than 0.001. So a 2K post hoc test revealed significant pairwise differences between fertilizer types 3 and 2, and with an average difference of 0.42 bushels per acre, that is P is less than 0.05, and between fertilizer 3 and 1 with an average difference of 0.59 bushels per acre, that is P is less than 0.01. I hope I was able to make you understand the statistical test of ANOVA, and one that especially one way ANOVA. Okay, but I have come across many people who often have doubts, and they frequently ask various questions. Like, what is the difference between one way ANOVA and a two-way ANOVA? Sometimes people ask, what is factorial ANOVA? How is the statistical significance calculated in an ANOVA? What is the difference between quantitative and categorical variables? So before I end this session, I will be answering to all these questions. Coming to the first question, what is the difference between one-way ANOVA and two-way ANOVA? So the only difference between one-way ANOVA and two-way ANOVA is the number of independent variables. A one-way ANOVA has one independent variable, while a two-way ANOVA has two. So one-way ANOVA, like testing the relationship between shoe brand and race finish times in a marathon. And two-way ANOVA example is testing the relationship between two shoe brand, runner age group, and the race finishing times in marathon. So all ANOVAs are designed to test for differences among three or more groups. So if we are only testing for a difference between two groups, we can use a t-test instead rather than the ANOVA. Then comes another group. What is factorial? What is factorial ANOVA? Factorial ANOVA is any ANOVA that uses more than one categorical independent variable. A two-way ANOVA is type of a factorial ANOVA only. For example, let's say testing the combined effects of vaccination, that is vaccinated or not vaccinated, and the health status, that means if a person is healthy or pre-existing condition on the rate of the flu infection in a population. Another example, testing the effects of marital status on job status and the family history on the incidence of depression in a population. Another example can be testing the effects of feed type, that is ABC, and barn crowding on final weight of chickens in a commercial farming operation. Coming to the last question, what are quantitative variables and categorical variables? So quantitative variables are any variables where the data represents amount, that is height, weight, or age, And categorical variables are any variables where the data represent groups. Like includes ranking. Okay. For example, brands of cereals, or you can say binary outcomes. So you need to know what type of variables you are working with to choose the right statistic test for your data and to interpret your results. Thank you, viewers. Have a good day. Now, before ending, I would like to answer the third question. So, in ANOVA, the null hypothesis is that there is no difference among group means. So, if any group differs significantly from the overall group mean, then the ANOVA will report a statistically significant result. Significant differences among group means are calculated using the F static. So, which is the ratio of the mean sum of squares to the mean square error. If the F statistic is higher than the critical value, the value of the F that corresponds with our alpha value, usually 0.05, then the difference among the groups is deemed statistically significant.